Welcome back to Math 103. This is video number 14 on voting. Last time we were applying the pairwise comparisons method to the following election, in which we found that Anne is declared the winner. Now suppose that after winning the election, she is disqualified for some reason. They've found performance-enhancing drugs in her system or whatever, and so we hold a revote. The question is, now who is the winner? There are now only 3 head-to-head matchups to consider. B versus C, we find that B is the winner. In the contest between B and D, there turns out to be a tie. You see these two and those other 2 voters, for a total of 4, have B higher than D, but these 4 voters have D higher than B, so this is a tie. And in the contest between C and D, we see that C is the winner. We have 1, 2, 3, 4, 5 out of the 8 voters ranking C higher than D. Great. So Bob gets 1.5 points total, Claire has 1 point, and Dave has just half a point now. So we conclude that Bob wins. Okay, so Anne won the first election, was subsequently disqualified, and now Bob is declared the winner. We ask, what conclusion follows from these results about the method of pairwise comparisons that changed the winner from Anne to Bob, and the independence of irrelevant alternatives criterion? Well, nothing follows. No conclusion follows because the IIA criterion does not apply in this situation. The eliminated candidate was the original winner. But this independence of irrelevant alternatives criterion only applies when the eliminated candidate was irrelevant, was someone who did not win the original election. If A is eliminated, if the original winner, Anne, is eliminated, of course there's going to be a new winner in the revotes. There is nothing irrational about the voting method just because we found a new winner in the revote. Of course we found a new winner in the revote. So where does this leave us? What have we discovered thus far? We have defined 4 voting methods. Each one has its own rationale. Each one makes sense from a certain point of view. Each of these voting methods, it turns out, we have discovered, sometimes violates at least one of our 4 fairness criteria. So we already knew that the first 3 voting methods we defined, plurality, instant runoff voting, and border count, sometimes violated the Condorcet criterion. We then devised a voting method, pairwise comparisons, so that it was never capable of violating the Condorcet criterion, and now it turns out that even that method goes wrong sometimes. Even that method now turns out to violate the 4th fairness criterion on our list. And that brings us to the really big question about voting methods in general. Is there a voting method which never violates any of our 4 fairness criteria? In other words, can we engineer a voting method so that it's guaranteed never to elect the wrong candidate, according to our 4 notions of wrong candidate as expressed by the fairness criteria? Now this is where mathematics, as such, really comes in. Kenneth Arrow proved in 1949 that there is no such voting method. For this work and for other work, he actually won the Nobel Prize in Economics in 1972. So here's Arrow's impossibility theorem. It states that for every voting method, there is at least one fairness criterion of the 4 that we have discussed, which that voting method sometimes violates. This is a mathematical theorem. Arrow proved it, and because he proved it, mathematics did more than state an opinion about what kinds of voting methods we could possibly think up in the future. He actually proved something. He removed all doubt about what kinds of voting methods could possibly be devised in the future. Now it will be important for us to understand just what it is that this statement does say and what it doesn't say. Now here's an important caution. Arrow's theorem is not saying that in every single election there's a violation. It's also not saying that democracy is unfair. It does not imply those things, even though some students come away from a course like this mistakenly thinking that that's what Arrow's theorem says. So what does Arrow's theorem say? What does it imply? It implies that no voting method can be engineered, no matter how smart we are. No voting method can possibly be engineered so that it is guaranteed to avoid violating any of our four fairness criteria, ever. Okay. Every voting method will sometimes produce violations. Let's try and clarify that further. Sometimes violates should be thought of as meaning eventually violates. So what that means is that if you look at a specific voting method, you take that voting method and you apply it to a large collection of preference tables, or pairs of before and after preference tables with regard to the second two fairness criteria, then that voting method will eventually violate one of our four fairness criteria. If you keep applying it long enough to enough different elections, eventually there will be a violation. Or to put it yet another way, you tell me which voting method we're talking about, I can go and find an example of an election in which that voting method does violate something, one of our fairness criteria. Now that might seem depressing, so where does Arrow's theorem leave us? Well, in spite of this seemingly dire mathematical result, the fact is there are very good reasons why each of the methods we've considered in this course, as well as many other variations, are used in specific situations. There are many, many voting methods besides these four. Okay. And each one has a certain rationale behind it and certain good reasons why you would want to use it. So, for example, the plurality method is very familiar and very simple. That offers certain advantages. We've seen advantages to instant runoff voting and Borda count and pairwise comparisons in that they all take into account, each in its own way, nuances of the voters' relative rankings of the candidates. Now, usually, the decision of which method to use is based on what seems most appropriate for the situation in which that voting method is applied. Let's conclude with some follow-up questions about Arrow's theorem. If someone devises a voting method which never violates the majority, Condorcet, or IIA criteria, then what follows? What can you say about that voting method? Question number 2. Suppose that someone devises a voting method which never violates the majority, monotonicity, or IIA criteria. So now an election is held, and there is a Condorcet candidate. What can you say about the election result? And B, if you apply this same voting method to many different elections, each of which has a Condorcet candidate, what will eventually happen? So Part A is asking about a single election, Part B is asking about many elections. Finally, question number 3, a pair of true-false questions. So A, true or false. Suppose that you read about a recently invented voting method which never violates any of the four fairness criteria. Then the author must have been mistaken about the method. True or false? Then question B, true or false, an election is held using a certain voting method. At least one violation must have occurred. True or false? Please answer these before going on to the next and final video.